And now we have, so we wanted in this conference to showcase the development of geometry in Oaxaca. Now the UNAM has opened this fabulous branch here in Oaxaca, and they have a lot of young people working in geometry, and I'm sure going to become a very important center for geometry in Mexico and internationally. And we want to showcase what people are doing here in Oaxaca in geometry and topology and direct geometry and mathematical things. And so we will have the first of the local professors here at UNAM, Oaxaca, and he's Carlos Segovia, and he will be talking about self-dual configurations and finite.
I'm very glad to be here. I want to thank to Ernesto for the invitation and for the opportunity to give this talk. Well, this work consists of a curiosity that I think I had for more or less 2 or 3 years about some really was lucky that I found this work. And the first is self-dual configuration. I want to start what is called the Cremona-Richmond configuration. This was found by Richmond, some people from British, and also Luigi Cremona, the people from Italian. And this is, if you want to draw it very nice, it's just this configuration of pentagons. But for example, you can find this in the book of Principle of Geometry of Baker. Yeah. And I want to give some motivation for this configuration. For example, you can take 6 digits and you can arrange in 15 pairs of dots. That was called by Sylvester. And for example, 1, 2, but you consider that they are configuration. They are taken as the same as 2, 1. And they are arranged together in 15 sets of 3. So these are called synthemes. But also they are the same if you just permute the 3. And dots and systems, they have the following correspondence. Each system consists of 3 dots, and each dot belongs to 3 systems. See? So this configuration of points and lines, that the lines that are going to be the synthemes and the point is going to be dots, form this beautiful configuration, the Cremona-Richmond configuration. Yeah. This structure of configuration normally are denoted by a pair of M, C, and D, where it has M points and N lines, where D points belongs to each line, and C of the lines pass through each point. So we have this equality, and if we have that M and N is equal, the points are the same as the lines. So we have that C is equal to D, and you can just denote ND, and this is what is called a self-dual configuration. And for example, you can see the Cremona-Richmond configuration is the 15-3. Okay. If we want to give some geometric interpretation, we can just consider 6 points in the 4-dimensional space, taken the real 4-dimensional space, and there are 15 lines that are denoted 1, 2, 1, 3. Yeah? There are 20 planes, and 15 hyperplanes that they are denoted just by these words. Yeah? And this structure, in the same way that gives the dots and the systems, there you can consider the points by P1, 2, just as the intersection of the line 1, 2 with the hyperplane that is consists of the disjoint letters with 1, 2. No? And this gives just one point in the 4-dimensional space. So the systems now, there are 15 lines, such as P1, 2, P3, 4, P5, 6, and this gives some structure that was studied just one century ago by Sylvester, Baker, Coxeter also. But I want to give another interpretation, and this interpretation comes in finite geometry. Then, for this, I recall the concept of the dual pole space, that for this we consider a symplectic vector space B of dimension 2n over the F2 vector space of 2 elements. And we say what is a subspace is a totally isotropic if just is contently completely in the orthogonal complement. So when we have the maximal ones, this is what is called now Lagrangians. Yeah? And this gives you the identity between U and the complement, the orthogonal complement. And this satisfies the following property. Every maximal total isotropic subspace has dimension n. Yeah? Indeed, all the maximal isotropic, total isotropic has the same dimension, and every maximal isotropic subspace of dimension n-1 is contained in exactly 3 different maximal totally isotropic subspaces. So, what is the geometry of this structure? No? This structure fits into the following, into a partial linear space, which satisfies that any line is at least incident with 2 points. There is a line is not defining only with 1 point. And any pair of distinct points is incident with at most 1 line. So there are not, for 2 points, we don't have that past 2 lines. No? And so this structure, yeah, called the dual polar space, consists of the maximal total isotropic spaces as points and the lines as the total isotropic subspaces of dimension n-1. So we have a configuration of points and lines where every line has 3 points. Yeah? And also another concept is what is the collinearity graph. This is a graph that is associated to this partial linear space where you have a configuration, but you want to associate a graph. So to every line that has 3 points, then you have to add the adjoining edges. So, for example, in n equal to 1, just you have 3 points and 1 line, then you have the following configuration. But if you want to associate a graph that shows the collinearity, then you have to add the following edges. You have a triangle. Yeah? And this is just the definition of the collinearity graph. Yeah? The vertices is just the points, and the edges is defined by the collinearity. So, and we have the following n-gon properties, because at the end I want to show these properties of finite geometry. The first is that we can choose a point, for example this, and we can say which are the points at distance 0, is just this, see? And this we are going to denote by gamma 0, and the points at distance 1 pues are these. Yeah? So an element is at distance k if only the dimension that you take for the intersection with the fixed points is n minus k. So, and you have a partition of your graph. So every line, also the second property is that every line contains 2 elements of gamma k and 1 element of gamma k minus 1. So I want to show, for example, you can have these graphs, no? Because what happened, for example, for this? Yeah. For example, for this, yeah, you can show that the connected components of gamma k coincide with the vector space of dimension k. So here you are going to have that the elements connected with x0 have to be 2 and not 3. That, for example, we have 3. And for example, here, yeah, we are going to have that for this point and this point pass 2 lines, and you don't want that. It's not a geometry. Yeah? And this by the n-gon properties, it does not satisfy. So, and also I show here what happened, for example, gamma with n1, which is a triangle, as I show here, no? But for n equal to, yeah, you have the Cremona-Richmond configuration, and you want to also to associate some graph, and the graph you can just join these three graphs, yeah, when you join the red ones with the red ones, the black ones with the black ones, and also you match the colors of the edges, and you have a really big graph of 14 edges and 15 vertices. Yeah? So, also, what I'm interested is to make configurations of bigger degrees, no? So when you take, for example, not equal n equal 2, but for example, yeah, for n equal 3, yeah, you have 135 vertices. So it's really difficult to understand what is the geometry. Yeah. So, but I use some computation in Sage, and for example, the first components, the componented components at distant 1 are these. At distant 2, yeah, is this cube, and you can see. So, for example, take the Richmond-Cremona configuration and take these fixed points, yeah? And you take the elements at distant 1 are this, and this, no? And the connected components are this, and this, no? You have three, vector space of dimension 1. And you have the elements at distant 3 are these 8 points. And when you see the graph of the collinearity graph, this form at a cube. Yeah? But for example, for the next degree, you have 7 cubes, yeah? And this is a distant 3. It's really complicated. So, and you want to make this more tractable. So well, and just the last concept I want to define is what is some dimension associated to this configuration. Yeah? An embedding of some configuration, yeah, is a vector space and a function to the vector space, yeah, such as that E is generated by the image, yeah, and the lines, we suppose that they have a length 3, they satisfy that they are projective. Yeah? The sum of the elements is 0. Yeah? So the universal embedding is the biggest. So you just make the quotient of the vector space generated by the points, by the quotient by the lines. Yeah? And you want to calculate this dimension. Yeah? And for example, what should be the dimension for the dimension for UG1? Yeah? If you have that they are projective, then you choose just 2 points, yeah? And you have the third. And this is the rule. If you have a line, you choose 2 points and you have the third. Yeah? But for example, for n equal 2, you can calculate these are the maxima total isotropic, and this is the total isotropic. These are the points, and these are the lines. No, sorry, it's equal because they are subdual. Yeah. So this is the points, and this is the lines. And the next dimension is 5, and then what does it mean? Okay? It means that if you can take 5 points there, and with the rule that if you have 2 points in one line, then you have the third. So, for example, here, suppose that I take these 4, B, O, G, H, and you take G, no? Then you have F, L, then you have C, you have K, you have N, then you have A, and you have, well, at the end you have A and H, no? Yeah. With only 5 points, you can generate all the configuration with this dimension. But the problem, what I was interested is to prove that if we increase the n, then this dimension is equal to this value. Yeah? And this value is 2, 5, 15, 51, yeah, and we can follow, no? But that was something that was in my PhD thesis, and when I put it in the, we can skip. If you put this value in the web page OAs, then you can find a lot of interpretations. Yeah? Mine was the last, yeah? Because this point was the zeta 2n covariance invariant, that at the end was some rank of some fundamental group. But this has also the following interpretation: is the density of a language with 4 letters, is the dimension of the universal embedding of the polar dual space, the number of non-equivalent states of a Hanoi graph, the dimension of the centralized algebra where H1 is a group of order 96, the number of isomorphic classes of regular 4-fold covariance of a graph L with Betti number BL and voltage group zeta 2 cruz zeta 2. Yeah? So at the end of this talk, I want to show the implication of this dimension associated to this configuration, and I show you this map for you. Because all these interpretations, yeah, what I was starting is this side. So this was the Cremona-Richmond configuration, yeah, when the inside hexagon is when you take just the field with 2 elements. But then, in some moment, we say, well, yeah, I'm going to talk about these different definitions. What happens if you take every field with P supposed prime? No? So for example, here you can have 4 covariance of regular graphs. Yeah? Here are the language with 4 letters and the Hanoi Tower. So let me just very quickly say you what is everything. No? So, for example, just recall the sequence and the language with 4 letters that you take 4 digits, 2, 3, 4, and then you say, well, let's take a language and put some grammar. For example, you take all the letters or the words, A1, A2, A, when you say the following grammar. A is minus that O equal, mayor que 0, that the maximum of the HG plus 1. So, for example, here, then this language, pues you can take the length of the word, and then you, for example, say that Ln are all the words of length n. So if n equals to 1, this has to be 1. No? If n equals to 2, you should have 1, 1, and 1, 2. Yeah? If you have n equal to 3, it's 1, 2, and 3. It's 1, 1, 1, 1, 2, 1, 2, 1, 1, 2, 2, and 1, 2, 3. So you have 5. Yeah? But the interesting is that you will have also these numbers that you will have for the Cremona-Richmond, you have 5. No? For example, what happened if you, with the Hanoi Towers, no? This is the interpretation with language. Yeah? So with Hanoi Towers, you can consider the usual game of Hanoi. Yeah? And suppose that you have the following graph. Yeah? Let me do it here. The vertices are going to be the states of Hanoi. So, for example, suppose that we have just the Hanoi, this game, but only with one disk. So, and you number the pegs 1, 2, 3. So, the Hanoi movements are going to be the edges. So, you have just a triangle. Yeah. But suppose that we put another disk, no? Where I leave the here, no? Yeah. So you will have different, no? You will have this, and you will have this, no? So, for example, no? But you will have, for example, this is going to be 1, 1, 2, 2, and 3, 3, no? So you will have this, but also the other movements are going to be just different elements that are going to be assigned where is essentially the disk this will form just some Sierpinski triangle, yeah. But suppose that now this at the end you will have also some Sierpinski triangles. This is going to be the graph, yeah, of this game. But suppose that you have that they are the same if you permute the pegs. So you will have also for this, it's just if you permute the edge, you will have that the isomorphism is going to be just 1. For this, you will have that this and this are the same. But all these are the same. You will have 2. And for this, you will have also 5. Yeah? Well, and just the last, yeah, is with coordinates, yeah. And for this, you take a coordinates, yeah, category, yeah. And just to say is that you have 2 generators, yeah. And you take elements in zeta 2 to the n, yeah. And just to show, you consider category COF with zeta 2 to the n, yeah. And you calculate the fundamental group of the classifying space of this, and this will have this value, yeah. This value that I show you, that is going to be 2, 5, 15, yeah, 51, yeah. And with that, I go from everywhere to any other side, yeah, yeah. But it's missing, for example, this, no? What happened with this, no? And to go to this structure, what we do is that the words they are classified in 7 families, yeah. And we have there are some vector spaces of the fixed space that I take x0, yeah. And we apply some Gauss-Jordan elimination to these vector spaces, and they coincide exactly with this structure, yeah. Well, I think with that I'm done. Yeah.
We continue in 5 minutes.